Hello everyone. So today we're going to go over section 6.2, characteristics of the equations of polynomial functions. So first we have here the standard forms of the polynomials functions that we'll be looking at. So we have the linear function, the quadratic function, and the cubic function. Now the one that is not included here, we also will be looking at the constant function. So that will be just the constant function, and you would have the form of f of x equals a, where a is of course just some number, and this would be degree 0. So of course we have linear functions that are of degree 1, quadratic functions of degree 2, and cubic functions are of degree 3. Okay, so um, again, we will be quite familiar with the linear and quadratic functions already. Cubic functions are new. So what we have here are some sketches of graphs of polynomial functions of degrees 1, 2, and 3. These are done using graphing calculators or in some cases in Desmos. Again, so you can also just go ahead and try to graph these on Desmos, but these are already prepared, so we're just going to go through them quickly together. So here we have f of x equals to 1 half x minus 6. So this, of course, you recognize as slope-intercept form, where the slope of the graph is 1 half and the y-intercept is 6. So m equals to 1 half and b is equal to, oh, actually negative 6. So as a positive slope, 1 half is still positive, of course, and then the y-intercept is negative 6, so you can see the sketch of the graph right here. Likewise, right next to it, we have negative 5x minus 2. So in this case, the slope is negative 5. So the graph will be moving downwards from, or decreasing from left to right. And the y-intercept, of course, in this case is negative 2. And then we have our first quadratic function, f of x equals to negative 2x squared plus 2x plus 4. So what we can do with this function here is we can actually factor out negative 2, and then we'll be left with x squared minus x minus 2, which of course you can factor. You can x minus 2 as one of the factors, and then x plus 1 as the other factor. So, based on what you have learned before in either pre-calculus or in Foundations 11, um, you would know that the x-intercepts are 2 and negative 1. And because the constant is 4, we can see that the y-intercept is 4. And the fact that this is a negative leading coefficient means the graph is pointing downward. So um, the graph that we have here is consistent with all those properties that we just described. Now, of course, sometimes you have quadratic functions that are not going to be factorable. We have x squared minus 6x plus 12. That's not going to be factorable. It is pointing upwards, and the entire graph is above the x-axis, so it has no x-intercepts. But we do know that the y-intercept is the constant value of 12. Okay, so the best way to approach these questions is to look at what they look like on Desmos or on the graphing calculator, and then determine the properties that way, um, rather than trying to factor them in every case, although that would also work. Now moving on to cubic functions, these are a little bit more unpredictable. Some of them will have 0 turning points, as we mentioned before, and some of them will have 2 turning points. But there are some characteristics that you can identify. So for example, if you look at these example here, the leading coefficient is negative 2. So it must be decreasing from going from left to right. May have turning points in between, but the overall picture is that it is going to come from quadrant 2 and end up in quadrant 4. And then, of course, the constant would tell you what the y-intercept is. In this case, it is going to be 1. the example right next to it, 2x cubed plus 4x squared minus 3x plus 1, that example, it has a positive leading coefficient, so it's going to be increasing as you move from left to right. So it's going to come in from quadrant 3 and then quadrant 1, and its y-intercept is just going to be 1. You'll notice that these two graphs, even though they're very similar algebraically, there's only one difference. One leads with -2, the other one leads with 2. But the first graph has no turning points and the second one has 2 turning points. So you really have to use a table of values or graph it using Desmos or graphing calculator to kind of see what the properties really are, um, for now at least. So finally, we have some more examples. You can see that the turning points can vary greatly. In this case, oops, comes all the way up to here. And then it actually has a 2 x-intercepts, which is interesting. We haven't had one of those examples yet, a cubic um, polynomial with exactly 2 x-intercepts. In this case, it does. Um, so, and then the next example, x cubed minus 8. You can see the y-intercept is -8. It is positive, so it slants upwards from left to right, and it has a single x-intercept. Okay. And finally, the last example, -x cubed plus 2x squared plus 15x minus 10. That one has a negative leading coefficient of -1 and a y-intercept of -10. And you can see that it behaves kind of what we had described from the previous example. So the really important information for you to glean from these 9 graphs is a couple of things. Number one, the constant term of a polynomial function is the y-intercept. So if you have something like, let's say f of x equals to 3x minus 7, then the y-intercept will be -7. Okay, so the other important piece is about the leading coefficient. Now, the shape of the graph, the end behavior depends on two things, the degree and also the leading coefficient. The leading coefficient at the very least will tell us where the graph ends as we move from left to right. So there's two possibilities. If you have a positive leading coefficient, then the graph is going to end in quadrant 1. If the graph has a negative leading coefficient, then it will end in quadrant 4. Okay, and then the other additional piece of information is if the degree of the polynomial is even, then the graph, in terms of its end behavior, is going to move horizontally across. And if it is odd degree, then the graph will move diagonally across the plane. And we'll have more example of that on the next page. All right, so we have here the degree of the polynomial determines the shape, as you know already. Degree 1, the linear function will be straight lines. Degree 2, so those are quadratic functions. They will be parabolas. And then the cubic functions will be of the different shapes that you saw on page 1. Okay, so we have some quick examples here about the different characteristics. So we can look at the function itself first. So let's look at example 2a. We see we have f of x equals to 3x minus 5. So it has a positive slope and a y-intercept of -5. Okay, so a sketch is already provided to the right. This graph would have one x-intercept. Now, generally, we'll not ask for what the x-intercept value actually is. It would just ask for how many x-intercepts there are. It also has one y-intercept. Now, y-intercept, you know the value of, and that is, of course, just a constant. So in this case, it is at y equals -5. The domain of all these polynomial function is going to be x is an element of all the real numbers. As you can see, this is a straight line, so it will span the entire plane. So range is always, the range is also going to be y is an element of the real numbers. Now, end behavior. Now, we know because of the fact that this has a positive leading coefficient, it will end in quadrant 1. So that part is easy. Now, because this function has odd degree, it's degree 1, is it's going to span diagonally across the plane. So if it's going to end in quadrant 1, it should come from quadrant 3. And you can see that our graph is consistent with that. And has no turning points because it is just a straight line. So those are the characteristics that you need to kind of be able to figure out. Sometimes based on just the equation, sometimes you'll be provided with the graph, and it makes it a little bit easier. Next up, we have a quadratic function. So it will be a parabola you can see on the right. In this case, it has two x-intercepts. Now, sometimes if you just look at the equation, it's very hard to tell because there are actually three possibilities, right? It could have 0 x-intercept, 1 x-intercept, or 2 x-intercept are possible for quadratic functions. But this particular quadratic function has a positive y-intercept, and it is pointing downwards because of the negative leading coefficient. So no matter how you draw, it's going to have to cross the um, x-axis in two different places. Okay, next up we have the y-intercept. Of course, we know that this is going to be a single y-intercept at y equals to 8. Again, as usual, the domain is x is an element of the real numbers. The range. Now, the range of the quadratic functions will be restricted, of course. So it's not going to be all real numbers. Now, unfortunately, in this case, we don't know what the maximum value of this parabola is. So all we can really say is that the y value is less than or equal to whatever the maximum value was. If we were given the vertex of this parabola, obviously, then we can tell what the maximum value is, and we can be more specific as to what the range is. Next up is the end behavior. We have a negative leading coefficient, so the graph is going to end in quadrant 4. Uh, and the graph is even degrees, so it will move diagonally across the plane. So it's going to come in from quadrant 3 and end in quadrant 4 as we move from left to right. And being a parabola, it has a single turning point, so that's just 1. All right. Next up, we have a cubic function. In this case, it is positive. Now, in this particular case, this has 3 x-intercepts. But as you know from the last day, it could have 1 x-intercept, 2 x-intercept, or 3 x-intercepts, depending on the on the shape of the actual graph. Just gonna match the colors here a little bit better. 3 x-intercepts, but it could have been 1, 2, or 3. If we only knew that it was a cubic polynomial, then it could be 1, 2, or 3 x-intercept. In this case, there are 3. You can see on the graph here. The y-intercept is -10. All these graphs will have a single y-intercept, so usually what we would ask for is just the value. And the domain of all polynomial functions is x is an element of the real numbers. The range, you can see that the graph actually spans the entire um, all of the y values, so y is an element of all the real numbers as well. There's no restrictions there. The end behavior, now because it is positive, right, the leading coefficient is 2, um, we know it ends in quadrant 1 and has an odd degree, so it's going to move diagonally across the plane like it does here. So this will be from quadrant 3 to quadrant 1. And finally, in this case, it has one turning point. Sorry, not one turning point. It has two turning points. But for cubic function, uh, that could be 0 or 2, depending on, again, the actual equation that we are given. Okay, so that is what we have for looking at the function of a polynomial to determine some of its properties. We generally will be using the degree, the leading coefficient, and the constant, which tells us quite a lot. It will tell us about the end behavior, the domain, the range for the most part, the y-intercept, and then the possibilities for the x-intercepts, and then the possibilities for the number of turning points. And of course, if you want more information, you generally will have to graph the graph or at least make a table of values. Okay, so there's more to this section, but that's all for today. Thank you for listening.